This video we're going to talk about something called the rational zeros theorem and its relationship to polynomial functions and zeros particularly. This theorem here is probably one of the bigger theorems you'll see in pre-calculus, as it helps you find the zeros of polynomial functions, but not all the zeros. It helps you find all of the rational zeros. And if you remember rational numbers from back in grade school, elementary school, and in your algebra careers, rational also means fractional. So this theorem here is going to help us find all the rational zeros. Could a polynomial function, have irrational roots or zeros? Yes, but this theorem will not give us the irrational zeros. It's going to give us only the rational zeros. So the theorem goes a little something like this. If we have this polynomial function here, it has degree n, it has these leading coefficients, these coefficients here, and a constant at the end. Degree n, these are all integers, these integer coefficients, and this last term is not zero. Then we could find all rational zeros of this polynomial function because they're going to have the form p divided by q, where we have some stipulations on p and q. P and q have no other common factors than positive or negative 1. The value of p is a factor of our constant, a sub 0, and q is an integer factor of our leading coefficient, a sub n. Now, the special case, if this leading coefficient is 1, then any rational zero that the polynomial function will have will just be factors of the constant term a naught, a sub 0. Now, all this stuff in theory makes sense, but when we boil it down to an example or two, we're really going to figure out what these values of p and q are and how they're used to find these possible zeros. Right, so let's do an example with the rational zeros theorem. Suppose we have a polynomial function f of x equals x to the fourth plus 4x cubed minus 12x minus 9, and we're asked to find the rational zeros of f of x. We're only looking for the rational zeros, not the irrational zeros. So what we do here is we look at our last term here. It's negative 9. So we're looking for our factors of negative 9. Right? Now our leading coefficient is 1, so we don't have to worry about finding our factors of positive 1 yet and doing any division. That'll be the second example that we do. All of our factors of negative 9 are positive and negative 1, positive or negative 3, and positive or negative 9. And these numbers right here are all the possible rational zeros of the function f of x. And what we do here is, to test and see which ones are zeros, we use the factor theorem in synthetic substitution. So if we do that, let's do synthetic substitution. We'll just go down the line. Positive 1, negative 1, positive 3, negative 3. We might have to do this 6 times before we come up with a 0, if we come up with the 0. And the good news is, once you have 1, we can use its resulting polynomial as a depressed polynomial to find the other zeros. So let's look at positive 1. Right? Positive 1. We do synthetic division here with positive 1. Write our coefficients. We have positive 1, positive 4, 0, negative 12, and negative 9. And in our remainder slot, we want this to be 0. If we get a remainder of 0, that tells us that root, or that possible value, is a factor. So let's do this synthetic division and hope to get a remainder of 0. Let's bring the 1 down. 1 times 1 is 1, 4 plus 1 is 5. 1 times 5 is 5, 0 plus 5 is 5, 1 times 5 is 5, negative 12 plus 5 is negative 7, negative 1 times, or positive 1 times negative 7 is negative 7, add the last two up, negative 9 and negative 7, and you get negative 16. Unfortunately, that remainder is not 0, so positive 1 is not a factor. Let's test out negative 1 now. Let's go down the list. Positive 1, we did positive 1, let's do negative 1. Alright. Negative 1 times 1 is negative 1. 4 plus negative 1 is 3. 1 times negative 3, 1 times negative 1 times 3 is negative 3. 0 plus negative 3 is negative 3. Negative 1 times negative 3 is positive 3. Negative 12 plus 3 is negative 9. Negative 9 times negative 1 is positive 9. Negative 9 plus 9 is 0. And we get a remainder of 0. So that tells you that 1 0, or one rational 0, is at x equals negative 1. Let's see if we can add anything else to that list. So now that we use this synthetic substitution, let's look at this polynomial here now. This polynomial is x cubed, because it has to be 1 less than the degree of the original polynomial function, plus 3x squared minus 3x minus 9. We're going to test the rest of these, positive or negative 3, positive or negative 9, on this polynomial. This polynomial right here is something called a depressed polynomial. This is the original polynomial function. This is a depressed polynomial function. So let's test positive 3 on this depressed polynomial. Do it over here. Write our coefficients up. 1, 3, negative 3, negative 9. Bring that 1 down. You get 1. 3 times 3 is 3. 3 plus 3 is 6. 3 times 6 is 18. Negative 3 plus 18 is 15. 3 times 15 is 45. Negative 9 plus 45 is 36. We want a remainder there of 0, so that does not work. Now let's try negative 3. Let's try negative 3 and see what we get. And we want a 0 right here. Negative 3 times positive 1 is negative 3. Negative 3 plus negative 3 is 0. Negative 3 times 0 is 0. Negative 3 plus 0 is negative 3. Negative 3 times negative 3 is positive 9. Negative 9 plus 9 is 0. So negative 3 is also a rational 0. And now look at what happens here. In this new depressed polynomial, we get x squared plus 0x minus 3. Or x squared minus 3. If we solve this equation here, we're going to get an irrational 0. We'll get x squared equals positive 3. And if we take the square root of 3 is irrational. So our only two rational zeros are negative 1 and negative 3. We can go ahead and test positive or negative 9 in this original polynomial, but in this original synthetic division, but you'll find that it doesn't work. So you might have to do this 2 or 3 times in order to get the right answer. but just know that there's only two rational zeros for this first function f of x. Second example here, we have the function g of x equals 2x cubed minus 7x squared plus x plus 10. Let's find the rational zeros here. First thing we do, look at our factors of positive 10. Alright, and then we divide it by the factor of our leading coefficient. Because it's not 1, we need to account for that leading coefficient of 2. Okay. All of our factors of 10, positive or negative 1, positive or negative 2, positive or negative 5, and positive or negative 10. Our factors of 2 are positive or negative 1 and positive or negative 2. Now we have to take care of all possible quotients here. So all of our possible zeros, all possible rational zeros, are as such. Positive or negative 1 divided by positive or negative 1 is positive or negative 1. We have positive or negative 1 divided by positive or negative 2. That's positive or negative 1/2. Positive or negative 2 divided by positive or negative 1 is positive or negative 2. Positive 2 divided by 2 here, regardless of its positive or negative here, is going to give you positive or negative 1. So that's a repeated 0. Positive or negative 5 divided by positive or negative 1 is positive or negative 5. Positive or negative 5 divided by positive or negative 2 is positive or negative 5/2. Positive or negative 10 divided by positive or negative 1 is positive or negative 10. And positive or negative 10 divided by positive or negative 2 is going to be positive or negative 5. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible rational zeros. Alright, and we're going to start checking all of them at the same time. We're going to check all of them by themselves. Except what I'm going to do is I'm going to check the integer ones. I'm not going to deal with the fractions ones yet because they get a little funky. So I'm going to check positive or negative 1. If we find it to be one of those, we'll keep going. If not, I'll use positive or negative 2 and positive or negative 5. Alright, so if we say a 0 is possibly 1, we'll do synthetic substitution and hope to get a remainder of 0. 2, negative 7, 1, 10. Bring the 2 down. 1 times 2 is 2. Negative 7 plus 2 is negative 5. 1 times negative 5 is negative 5. Negative 1 plus negative 5 is negative 4. 1 times negative 4 is negative 4. 10 plus negative 4 is 6. We don't have a 0 here. So we need to keep going here. Let's look at negative 1 now. Negative 1 times 2 is negative 2. Negative 7 plus negative 2 is negative 9. Negative 1 times negative 9 is 9. 1 plus 9 is 10. Negative 1 times 10 is negative 10. 10 plus negative 10 is 0. So guess what? That value there, negative 1, is a 0. So possible zeros. So negative 1 is a 0. So all the rational zeros are at x equals negative 1. That's one of them. Let's look at others here. Let's use the depressed polynomial here to find some more. Instead of using this depressed polynomial like we did in the last example, let's write this as an actual polynomial function of degree 3 minus 1, which is 2. So this is going to be 2x squared minus 9x plus 10. Right? Because we found negative 1 is a 0, alright, if we multiply this polynomial here times the factor x plus 1, we will get our original function f of x. Right? And if we set this equal to 0, x plus 1 equals 0, so our factor, our one rational 0, is negative 1. So what we can do as sort of a shortcut, if you can, not all the time, you can't always do this, but sometimes you can, set this equal to 0 and factor it. If you can, fantastic. If not, you're going to have to go through these again with this depressed polynomial. Alright, and this can be factored actually. 2 times 10 is 20. Factors of 20 that add up to negative 9 are negative 4 and negative 5. So we get x minus 4 times x minus 5. Divide 4 and 5 there by the 2. Simplify them. 4 halves is 2. 5 halves can't simplify, so that 2 is going to slide in front of the x. And we can find our zeros by setting this equal to 0. This product here, x minus 2 times 2x minus 5, is equivalent to this trinomial. So if we set both of these terms equal to 0 on their own, we get x minus 2 equals 0. So x equals 2. 2 is rational. So another rational 0 is a positive 2. And then if we set this equal to 0, we get 2x minus 5 equals 0. So 2x equals 5. And divide, we get x to be positive 5 halves. So another rational 0 is at 5 halves. Now if you didn't do that to find the other two, don't worry, we could also do it by synthetic division. We could also do it by synthetic division. We could test positive 2 with this depressed polynomial. 2, negative 9, 10. And we want here, in our remainder spot, a 0. Bring the 2 down. 2 times 2 is 4. Negative 9 plus 4 is negative 5. 2 times negative 5 is negative 10. 10 plus negative 10 is 0. So we're left with 2 as a rational 0. This equation here, because it's linear, is 2x minus 5. Just set that equal to 0, and you'll get x to be positive 5 halves. And that's how you find these rational zeros, if the coefficient is something other than 1. Okay. Now, these problems, they do take a lot of work. They do take a lot of work, but they are nice. It helps us find all those rational zeros.